$1 million in prize money is on the line in the first ever head-to-head autonomous racing event to be held at the Indianapolis Motor Speedway in October. UVA Engineering's Cavalier Autonomous Racing Team will compete with other top universities for bragging rights as the best autonomous racing team in the world. Buckle up as I, your host, Chris Tyree, and UVA Engineering professor Madhur Bahel take you in the shop, under the hood, and around the track in this new world, pushing autonomous vehicles to their limits. Hello, my name is Chris Tyree. I'm at the UVA School of Engineering Communications Department, and I am excited to begin a series talking with Madhur Bahel, who is a computer science professor here at UVA Engineering and one of the leaders of autonomous racing in the world.
Yeah, Chris, thanks for that good introduction and for setting this up and inviting me. I'm really excited to chat more about what UVA is doing in autonomous racing and why this is such an exciting time to be doing this.
Let's just get started and hear a little bit more about where we're at right now physically, but also where we're at in this new challenge.
I am a professor in computer science. I also am affiliated with systems engineering at UVA. And then I work in the Cyber Physical Systems Link Lab, which is this beautiful space we are in right now. And as part of sort of what my group does is we work on a lot of problems of artificial intelligence and control applied to everyday use of autonomous systems. So in particular, we do a lot of research on safety of autonomous vehicles and robotics. As part of this same thought process, I'm leading and I'm the team principal for Cavalier Autonomous Racing, which is our university's competitive autonomous racing team. It's the first of its kind at this university. And then, as you rightly pointed out, we are one of the teams which is competing in this historic Indy Autonomous Challenge, which will culminate in a head-to-head, high-speed, fully autonomous race car going against each other from fellow other universities from across the world, and the team that makes it through 20 laps and crosses the line without causing a pileup or impeding other teams' progress will win $1 million. So yeah, that's pretty exciting.
That's amazing. Well, we're going to come back and cover all that in minute detail as we lead up to race day, which is October 23rd of this year. So let's just jump way back and maybe just talk about how did you even get interested in this in the first place?
Gosh, yeah. So way back I have to decide how far back are we going with this. But,
all the way back. I think when you were a toddler, I guess.
Yeah, I mean, they say about engineering and about scientists that there's this almost a stereotype that they tinker with things and they like building things and taking them apart, and I guess all of that is true for me as well. I was definitely I'm the first generation engineer in my family. I was a bit of an outlier in that respect, but I was always interested in technology and growing up. I think the tipping point for me was when I got introduced into robotics and understood what that is. And I think that feeling has never left me when I first saw, here's something that we build over nights and weekends, and now it just works on its own, and it's able to do, at the time, a very simple thing. We built a stair climbing robot, which was just like a motor with some metal legs, if you will, and it wasn't even that autonomous. But to see it climb an actual stair is, I think, what it's all about at the end of the day. That it's very gratifying to see that work, and to not just see it work, to understand why it works. One of the things that I can, maybe a singular event if I had to pinpoint, which maybe shaped the career path I took, it was in my senior year of undergraduate. I had an opportunity to spend 6 months doing a robotics themed internship at ETH Zurich, the Swiss Federal Institute of Technology. And not only was this the first exposure for me on here's how you do research, right? Because at undergrad, you are just too occupied doing courses and stuff, and you don't get that exposure to doing research. And working on an actual unsolved problem, and over there I've worked on like swarm robotics, so how do you control 50 different robots rather than one robot? And coming on the other side out of this experience, I was like, well, this is a viable, exciting path that I haven't even explored. And so that's what encouraged me to apply to graduate school and come here to the States to do my PhD from University of Pennsylvania. It added to my excitement with it provided the background and the mathematical maturity to get into robotics. So that I had a new appreciation. So not only building stuff is what I enjoy, but I also enjoy the theoretical aspects of designing new methods, which almost have a co-design with the hardware that you build in. So there I had my training in machine learning and controls and embedded systems, which you can call as the DNA of robotics and autonomous systems. To this day, I get equally excited as I did when I built that stair climbing robot. When I see these robots or other robots that we've built work autonomously, and now we are living through the age where AI and autonomous systems they are already very tightly knit into, I would say, the fabric of society. Right. And so I think either you could be a bystander and just see where it takes you in the next decade or so, or you could partake in shaping that future. And that's really my goal at the end of the day, to not only have an impact on a real world problem, but to train the next generation of students who will become leaders in this space. Yeah.
I remember getting this really fun robot. It was a Star Wars R2-D2 mm-hmm. that had a remote control that you could turn the head on and move it where you wanted and control it. And I thought that was the coolest thing in the world. Like we were moving into the next space age or whatever. But,
right.
So I think there's that thrill for everybody.
I am also in the same boat as being heavily influenced by science fiction and robotics and science fiction. In fact, being a autonomous systems and a roboticist guy myself, every time I meet a fellow roboticist, my first question to them is, which is your all-time favorite science fiction movie robot, right? So that's where the conversation starts. So yeah, at UVA, I joined in the fall of 2017, so just a little over 3 years ago. I joined here to set up this lab in cyber physical systems. We do a lot more than just self-driving cars in my research group. So we do all aspects of autonomy. At the end of the day, we want any autonomous system to be safe, and especially when it comes to doing tasks which one would consider as life critical or safety critical. So that expands beyond just a self-driving car. It could be robots in surgery or autonomous system that governs how a building operates and how the temperature inside that ought to be regulated so that the occupants don't feel discomfort and things like that.
All right, so we're going to jump back.
Okay.
And what was your favorite sci-fi robot? Come on.
I knew we were going to jump back. Okay, so I dig myself a hole there because I have maybe 4 or 5 favorites.
Okay.
And so let's get the obvious ones out of the way. So there's WALL-E, which is, I must apologize to Star Wars fans. I'm not going to name any of their robots, unfortunately. But then the less popular one, which I really like, not because of the ability, but because of the description of the robot, is a robot called Marvin the Android. It's from my all-time favorite book, which is The Hitchhiker's Guide to the Galaxy by Douglas Adams. And because that's a book, the robot is not really visualized that well, but it's described in such a nice manner that if I had to build one, I would build that robot, which is Marvin. And then there's others too. There's a adorable robot called Baymax from the movie Big Hero 6 a couple of years ago.
I love that movie.
The inflatable, huggable robot. I think that's everyone wants. And that's actually based off of real research in an area called soft robotics. So it's not completely in the realm of science fiction. And what else? Yeah, I think 2 others come to mind. One is again, a lesser-known robot called Gertie. It's from a 2009 science fiction movie called The Moon. Okay. And the thing I like about that robot in particular is that it only communicates through emoticons. And so I found that concept very powerful. It's kind of related to human-robot interaction a little bit. And then a robot called, I think, Taurus comes to mind from Interstellar, which is just two legs moving about.
Right.
So yeah, there's many more, but let's stop.
Well, I'm much older than you, obviously, because
Hal, I forgot Hal. Sorry to interrupt you. Hal from the epic movie 2001.
Oh, Hal, yeah.
A Space Odyssey. Yeah, how could I leave that out?
Right. I mean, that was, I think my very first kind of introduction to robots would have been Lost in Space. It seems like we've made a lot of advances just in the last decade, but maybe talk a little bit about that and sort of what are you doing here at UVA in that realm to really engage students?
Once again, if we have to point at what started this domino effect, I would most certainly think about the DARPA Grand Challenges, which were held in the mid 2004, 2005, I believe, was the first Grand Challenge, where they invited universities to drive autonomously more than 100 miles across the Mojave Desert. So very, very grand challenge, as the name implies, at the time, and very few teams were able to finish that task. And then there was a follow-on challenge, which was, okay, we can maybe drive by ourselves in the middle of the desert, but can we now drive on the road in an urban situation and follow the rules of the road along with other manual-driven cars? So that was a DARPA Urban Challenge, and again, it was a university, heavily, most of the teams were from universities. And in fact, many of the leaders or the winners of that challenge or the top teams, they are now, you can see them in the leadership of many companies today, which are working on building that autonomous vehicle that we all want, and it will solve a lot of our problems as well. So that's, I think, where it started, and it's funny to think of. At the time, I was just beginning my undergraduate studies. So since then, obviously, there's been a lot of activity. I think hardly a day or two goes by before you hear about another demo or another different ability or a feature upgrade. Sometimes you also hear about mishaps and crashes, so we have to pay kind of equal attention to both the successes and failures of this. But over the last decade, I would really say, is where things have started to transition from just being a research or a demonstration to transforming into an actual product that someone can buy. And you can only buy a Tesla today, and it's still a semi-autonomous car. It's not fully autonomous. But having said that, I think we've come a long way in the sense that the problem of driving itself is very complex. We humans underestimate how many years it takes us to get how good we get at it. But it's a pretty complicated task if you think about it. You're literally driving in a tin box on wheels along with others, and you are making very rapid decisions on trying to not crash and get to where you want to go safely.
I can attest to that because my son just got his learner's permit.
Right.
And we've been taking some rides, and my knuckles are like, permanently clenched. It takes everything to drive a car. You've got to be on.
Yeah.
There's no off. You can't be distracted or you're going to get into an accident.
Yes, absolutely. And I think that's part of the thinking behind this push for autonomous vehicles, right? So as good as we are at driving, as humans, we are also very deeply flawed by distress or by distraction or under influence or something like that. And that's the number one cause for accidents today, right? So a human is at fault, and then the second cause is maybe there's some mechanical or software failure. So if we could fix that, just the immediate impact in terms of preventable accidents and fatalities is alone sort of worth its weight in gold. I think there's nothing more valuable than saving lives, right? So I think that's definitely a big motivation. But I'm glad you brought the experience of driving with your son, because that's how we teach self-driving cars as well, right? There's a learning curve. It's like initially they do drive like a young driver with a learner's permit, so it's making mistakes and not aware of what's happening in adjacent lanes, or they're braking too hard or speeding unnecessarily. The follow distance is not correct. And so the autonomous driving or the autonomous driver has gone through the same transition. And really, this is a problem in some respects in artificial general intelligence that we are trying to solve. And driving is a very intelligent task, or a description of a task which requires higher intelligence. Today, we don't have the ability to drive from, let's say, any random address in downtown Manhattan to a random address in Boston. And so that's where the last 10% of problems have to be addressed. And these have to do with the messiness of the real world. There are situations which we experience in traffic that are unexpected, and you haven't thought through them of them when you were designing your software. So there's always going to be this set of, I would say, unknowns. And there's I would say, an infinite set of situations that can occur, and it's impossible for anyone to account for them beforehand. So that's a big problem. How do you design a software that can sense its surroundings, but also make decisions on situations that it has never experienced before, which is what humans also do when they're behind the wheels. So that requires almost like a breakthrough in the kind of algorithms and the machine learning and the traditional classical methods of designing motion planning and path planning. How it all comes together, how can it be verified and be safe at all times. So one of the biggest unanswered questions today is what is even a safe autonomous vehicle, right? There's no consensus on what people would consider an autonomous vehicle to be safe, because I can tell you today the safest vehicle is a vehicle which goes nowhere, it's just parked. And even that might not be safe, because someone can come and crash into you. So in many ways, I think what my work in particular does is this last 10% of the problems. We are explicitly trying to study how can we make vehicles safer by making them more agile. This is the bread and butter of autonomous driving. You have to react faster than what a human could do. And so to do that, you need to understand how this vehicle maneuvers at aggressive steering or aggressive braking. Do my wheels spin out? Do I lose traction? Do I drift out? We postulate that by teaching the self-driving car stack, or by incorporating the ability to be agile, you are actually enhancing safety. Now, I'm not implying that you are racing through traffic all the time. That would be not a good idea. But this is where the idea of racing comes in. How do you teach vehicles to be agile? Well, let's look at racing, because in racing, cars drive next to each other at high speeds in close proximity all the time. So it's the norm rather than the exception in racing. So if we can take a cue from how expert drivers race, we have a chance to learn how to be agile. And there's many issues. I'm kind of simplifying here, because I understand that race cars are not the same as cars on the road. They have different behavior and dynamics itself, but we are trying to capture the essence of this agility and then integrate it back to regular commercial driving. So you could say, what we are doing is bringing AI up to speed, because it has gone a certain distance where we can see some very convincing abilities, whether it's a Tesla or some other prototype, of them driving on a freeway and going from point A to point B without anybody having to touch the wheel. But it's not quite there yet, not to the extent where we can just say, okay, everybody can sit back and we don't need to drive anymore. Yeah, so the Cavalier Autonomous Racing Club is quite new. It's just a little over a year old, and thanks to some support from the Jefferson Trust Foundation, we were able to organize this. It's essentially a student-led club. I'm their faculty advisor. But we got into racing many years ago through this other sort of program that I led called the F110 Autonomous Racing. Right, so that's the car which is right beside me. Okay. It's a 1/10 scale version of a fully autonomous vehicle, or a race car in particular.
And you were doing that before you came to UVA?
That's correct. So it was a little bit of when I was transitioning out of my PhD and my grad school, we didn't envision that it would grow this to the scale as it is today. It stemmed from more of a hobby, and let's build a car that can drive around the hallway in our labs. And so we built the first prototype, and we were all surprised by how well it worked. And then immediately there was this recognition that this could be a very useful thing beyond just a hobby. How cool would it be that you can do all of that research in a controlled space inside the four walls of your lab? And I think that's what led to the idea that, hey, we should just open source the design of this car. So this car, if I can just show you a little bit, it's a 1/10 scale RC car, which is the chassis underneath, and then on top we have automotive grade plastic called ABS, which we laser cut in form of let's say the deck plate on which everything will be mounted. So this car has all the same sensors, just a different scale as you would find on a full scale prototype. So you have a LiDAR, and we also have cameras. This particular one is missing that. We have like a motor controller, and it has a high powered GPU computer, which is from the same family of computers that you find in full scale prototypes. So you could use this for designing all the perception, planning, and control algorithms that you would want to test in the real world. So it became this instrument from bringing your research from simulation and from theory onto a real test bed. And so I started that. I was one of the first people who started this as I was transitioning out. And then when I came to UVA, along with just bringing this for my own research, I'm very intentional about my mission to educate the next generation of students and researchers who will work in this space. And so I designed the first course on autonomous racing, right? So we had I still teach a course here at UVA. It's an undergraduate course called F110 Autonomous Racing. There are no exams in my course. The final exam is an autonomous race.
How many kids are getting turned away on a daily basis from this class? Like, it's got to be standing room only in there. Well, I guess normal times. We're in COVID now, and that's
correct.
why actually we're sitting apart with our masks on. But
yeah, I mean, in the class, students actually build the cars. They put it together, and then we teach them how these cars drive. And ultimately, we teach them how to race. And so even before the Indy Challenge, we were already big proponents of using competition as a basis to promote learning and education. And so the F110, checks all those boxes. And it's my favorite class to teach. I have a lot of fun doing that. And in the pandemic, we have switched to a simulation version of it, which admittedly is not as the same experience as building the real car, but it's still very useful to get at know the inner workings of how these cars work. So there's the research piece, there's the education, and then the final piece of the F110 is the community. And to build that community and this open source exchange of ideas, I have been also hosting international autonomous racing competitions at the top conferences in embedded systems and cyber physical systems and robotics. And we were again taken aback by, we have like dozens of teams from Europe, from Korea, from Singapore, showing up to these conferences. We never interacted with them, so they just look at our webpage where we have very detailed IKEA-style instructions on how to put this together with some code to help you out. And these teams show up, and everybody has the same car, and we didn't race, right? So we were doing autonomous racing since 2015, 2016. So there's a little bit of a lineage in terms of our own experience, which naturally for me was when I came to UVA, I have the course, so I can teach maybe 50 students a year, all of this stuff, and some of them then go on to either take a position in the AV industry or go to grad school in autonomy. But then I was still getting approached by students who weren't undergraduates, who wanted to still take the course, or they just wanted to do research in autonomous systems. And as a faculty and a professor, the thing I hate the most is turning students away for reasons which are administrative or logistic. So that's what led me to to think that we should just make this a university-wide initiative. So anybody who has the motivation and the time, which is also equally important, to devote to this should be able to have access to this opportunity. So that's where the idea for Cavalier Autonomous Racing came from, to make it a university-wide initiative, not just in engineering, but even beyond engineering is my goal. And the good piece of this is that the timing of this was such that it aligned very well with the announcement of the Indy Autonomous Challenge. And so now we have a mission, right? And we are all just spending weeks after weeks trying to build our autonomous racing driver that will now go from the 1/10 scale to maybe a medium scale, which is the go-kart behind me, and ultimately to the full-scale vehicle that will race at Indy.
So you guys are now gearing up for this challenge, a full-size Indy car,
correct,
to be raced at the Indianapolis Motor Speedway,
yep,
with a first prize of $1 million.
Yep.
The very first races were about making people feel comfortable,
right,
about transitioning from their buggies to
yep,
a four-wheel vehicle.
You are right. When we transitioned from, let's say, horse-driven cars to horseless cars, so now we are doing driver to driverless. Back in the day, it was different. The public was skeptical, and still there is data today. There's been surveys which say 3 in 4 Americans don't feel comfortable yet to putting their trust, right? So they were asked, would you allow your loved one to be driven from point A to point B, or would you allow a car to go and pick up your kid from school? And people just say, oh, no, not yet, right? So there is always going to be that issue of public trust and safety, and it goes all the way back to the very first race where people thought that engines are just going to blow up, or the cars will not stop, the brakes are not a proven technology. And so racing then became this idea, well, we can show you endurance, we can demonstrate safety. And talking about safety, majority of technologies which are present in the everyday sedan that you can buy, or any car, they can be traced back, their origins of each of these pieces, whether it's braking or any kind of safety gear, or the improvements in chassis design, materials. Many of these roots can be traced back to innovations in racing itself, right? So beyond just being a sport and entertaining, it has always been a way to spur innovation. The Indy Autonomous Challenge is that same idea, but extended to now the software stack, right? So in particular, the idea in the challenge is that all teams will get uniform hardware. So it's not about who has the most powerful engine or better tires and what have you. The emphasis is on outmaneuvering your opponent purely on the basis of your perception, planning, and control algorithms, or the autonomous driving stack. Make no mistake, right? Racing is unsolved, right? Autonomous racing is an unsolved research problem. There's no known solutions that teams are just going to port onto their vehicles and be happy with it. But there would be many pieces of these software advances which I think will have a long-term impact in shaping the safety of everyday autonomous vehicles. I say every day because I think in the future they might become much more ubiquitous than they are today. In motorsport racing, there is a saying that if everything seems under control, then you are not going fast enough. Right? That's let's say that's the thinking of racing drivers. And what we are doing is designing an AI algorithm with that as the goal, as the objective function, as they would call it. And so it's very difficult, but that's also where the excitement lies. Yes, the $1 million prize is appropriately large enough to reward all this effort, but I think for us academics and researchers, just the opportunity to be able to try these ideas in a real vehicle going in excess of 120, 150 miles per hour, that in itself is a little bit unprecedented, right? Not at the scale. And so there would be innovations in overtaking, innovations in understanding how sensor data appears at very high speeds, innovations in making high frequency decisions, which is all racing is about. You don't have as they say, the luxury of time to figure everything out, right? By the time you figure out what you will do on this coming left-hand turn, you're already there, right? So there would be very advances in software. So there's a long laundry list of things which we have to solve, and that's why we use simulation. So the competition has two parts, two phases. The first phase is all teams will race in simulation. So the stakes are low, but there will be a final simulation race come May of this year. And then starting from May, we will actually transition to porting all that knowledge and testing that we have done in the simulator onto the real car, and there's many problems that we'll have to solve when it comes to that. So we'll have some practice days at the Indianapolis track to fine-tune our methods, to make sure we can operate safely, because in racing, it's also about your safety is dependent on how others also behave. There's another, very famous quote, which is that to finish first you have to finish, right? So you can't all be just opportunistic to go after every opportunity. There's a very real risk of a crash happening, and nobody wants that, but it's there, and everybody is aware of this, and we'll do our best to not be the ones crashing or causing a crash. So yeah, I think the list goes on and on. I think very high impact, high quality research, high quality talent will come out of this competition, and like I said, it resonates with everything we do here at UVA, with my own research, but it's beyond just an individual's, I think, grasp to fully solve this problem, and that's why it takes a team of very smart individuals, which is what this competition is all about.
And just to be clear, the racers from UVA are primarily students, am I right?
Oh, yeah. So we have about more than, let's say, 12 students in our club right now. So it's expanding every 2 weeks, and they are an equal mix, I would say, of undergraduate students and graduate students. And yeah, they are the ones who are really shaping our racing algorithm. And so, we often say, like, installing drivers will have a new literal meaning after this race, right? So when we talk about software. And yeah, some of them are PhD level students who are experts in kind of trajectory planning, and overtaking is their sort of dissertation topic, if you will. But then there are others who are experts in software and simulation, in just developing, analyzing camera data or LiDAR data. We can have a whole different discussion on perception and sensing. And one of my students actually in the club, he has a history in racing, actual like human manual racing. So he has spent some time with the NASCAR racing team as a design engineer. And he's our in-house racing driver. We rely on him to, guide us and tell us about. Many drivers describe that when they drive with feel, right? So they can feel when the car is under control, when it's sitting firmly at that limits of control that I said earlier. So how do you capture that in an algorithm? What is feel for a mathematical function or a formula? And these are kind of the problems we are trying to encode, right? We have to encode a driver's years of experience and knowledge into some kind of a logical construct that we can build upon and automate. So yes, absolutely, this is 100% student driven. I think every week when we meet, that's the best part of my week, yeah.
Thanks so much for taking us under the hood of this awesome experience you have going here, and we're really excited for the journey ahead for you all.
Yeah, thanks, Chris, for again setting this all up and inviting me. This has been very enjoyable for me to chat about what we are doing here and what the ambition and the goals of this are.